Cloud Gateway Load Balancers Compared. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series, we are doing a deep technical comparison of gateway load balancers across the three major cloud providers: Amazon Web Services, Microsoft Azure, and Google Cloud Platform. If you work in cloud security, network engineering, or infrastructure architecture, this is a topic you absolutely need to understand. All three hyperscalers offer a mechanism for transparently inserting network virtual appliances, also called NVAs, into traffic flows without requiring changes to application infrastructure. The concept is powerful. Route traffic through a firewall, an intrusion detection system, or a deep packet inspection engine, and do so invisibly from the application's perspective. But how each cloud implements this differs significantly in architecture, encapsulation protocol, feature set, and operational model. By the end of this series, you will be able to design inline security architectures on any of the three platforms and understand the trade-offs that inform your choice. AWS Gateway Load Balancer. Core concepts. The AWS Gateway Load Balancer, commonly abbreviated as GWLB, was released in November 2020 and represents AWS's solution to transparent NVA insertion. It operates at Layer 3, meaning it understands IP packets rather than HTTP sessions, and it uses a specific encapsulation protocol called GNV, Generic Network Virtualization Encapsulation, to carry traffic between the GWLB and the NVA instances. The fundamental deployment unit in AWS GWLB is the endpoint pair. You deploy the GWLB itself inside a dedicated security VPC, which is where your NVA fleet lives. In the application VPC where your workloads reside, you create a gateway load balancer endpoint, which is a VPC endpoint powered by AWS Private Link. This endpoint appears in the route table as a next hop target, allowing you to steer traffic to the GWLB with a simple route entry. The diagram shows the three-zone architecture. The Internet gateway on the ingress side receives inbound traffic. A route table entry in the application VPC's edge or subnet route table sends that traffic to the GWLB endpoint instead of directly to the workload. The GWLB endpoint forwards traffic across private link to the GWLB in the security VPC. The GWLB encapsulates the original packet in a GNV tunnel and delivers it to a healthy NVA instance from the target group. The NVA inspects or processes the packet, then returns it to the GWLB through the same GNV tunnel. The GWLB decapsulates the packet and returns it through the private link path back to the application VPC, where it continues to the intended workload. Return traffic follows the symmetric reverse path. Critically, throughout this entire process, the source and destination IP addresses inside the GNV encapsulated packet are completely unchanged. The NVA sees the real source IP of the external client and the real destination IP of the internal workload. This is essential for security rules, logging, and threat intelligence matching. Azure Gateway Load Balancer. Core concepts. Microsoft Azure introduced its Gateway Load Balancer in November 2021, roughly a year after AWS. Azure took a philosophically similar approach: transparent NVA insertion using tunnel encapsulation, but the implementation details differ in meaningful ways that affect how you design and operate your security infrastructure. The Azure Gateway Load Balancer sits at the front end of the NVA fleet and uses a concept called chaining to link itself to a consumer load balancer. The consumer load balancer is the standard load balancer or the public IP address that your application VNet uses for inbound or outbound connectivity. When you chain a gateway load balancer to a consumer load balancer's front end, Azure automatically inserts the GWLB into the traffic path. This chaining mechanism is significant because it does not require route table changes in the consumer VNet, unlike the AWS model, which requires explicit UDR modifications. The diagram illustrates the Azure chaining model. traffic arrives at the consumer load balancer's public IP frontend. Because a gateway load balancer is chained to that frontend, Azure redirects the traffic through the gateway load balancer before it reaches the backend pool of the consumer load balancer. The gateway load balancer distributes the traffic across its own backend pool, which is the NBA fleet. Traffic flows through the NBA for inspection, exits through the return port, and Azure then delivers it to the original consumer load balancer backend. The application server receives traffic that has been transparently inspected. Azure GWLB uses VXLAN encapsulation internally, specifically a variant that Microsoft refers to as the Gateway Load Balancer Protocol, which carries both the internal and external traffic flows over distinct VXLAN identifiers called VNs. The NBA must be configured with two ports: an ingress port that receives traffic from GWLB and an egress port that returns traffic to GWLB. Azure calls these the internal and external ports in the tunnel interface configuration of the backend pool. Google CP's approach internal pass-through NLB with NBA pools. Google Cloud Platform does not offer a service branded specifically as a gateway load balancer. Instead, GCP achieves transparent NBA insertion through a combination of its internal pass-through network load balancer and policy-based routing, sometimes referred to as PBR. This approach has been the foundation of GCP's NBA integration story, and while it achieves functionally similar outcomes to AWS GWLB and Azure GWLB, it operates through different primitives. The internal pass-through network load balancer in GCP is a regional, non-proxied load balancer that operates at Layer 3 and Layer 4. Non-proxied means it does not terminate TCP connections or NAT source addresses. It passes packets through to the backend with the original IP headers intact. This characteristic is precisely what makes it suitable for NBA inspection deployments, because the NBA sees the genuine source and destination IP addresses of the traffic it is inspecting. The diagram shows the GCP NBA insertion model using policy-based routing. Traffic arrives in the application VPC and matches a policy-based routing rule, which is configured on the VPC network or subnet to intercept specific traffic and forward it to the internal load balancer's forwarding rule IP address as the next hop. The internal pass-through NLB distributes that traffic across the NBA instance group using a connection routing-based hash to maintain flow affinity for stateful appliances. The NBA inspects the packet and returns it. Return traffic from the NBA is injected back into the VPC routing fabric, where it continues to the original destination. The key difference from AWS and Azure is that GCP's model does not use a dedicated tunnel encapsulation protocol between the load balancer and the NBA backends. Traffic arrives at the NBA with original IP headers, without Geneve or VXLAN wrapping. This simplifies NBA configuration. Your appliance software does not need to handle encapsulation or decapsulation, but it means GCP relies on routing discipline and health checks rather than a dedicated control plane tunnel to manage the traffic path. Feature comparison: AWS versus Azure versus GCP. Now that we have covered the architecture and configuration of all three platforms in depth, let us consolidate the comparison into a structured feature matrix. This will help you quickly identify which platform's capabilities align with your specific requirements. Looking at the encapsulation protocol row, AWS uses GNEVE on UDP port 6081. Azure uses a VXLAN-based dual VNI tunnel interface model, and GCP uses no encapsulation for its inline model. Traffic arrives at the NBA with original headers intact. This has a direct implication for NBA software compatibility. Many commercial appliance vendors support GNEVE for AWS, the Azure Tunnel Interface model for Azure, but for GCP you may find simpler configuration because no decapsulation logic is required. On the traffic insertion mechanism, AWS requires explicit user-defined routes in the application VPC's route table pointing to the GWLB endpoint. Azure uses the chaining model tied to a consumer load balancer or public IP frontend, requiring no route table changes. GCP uses policy-based routing rules or explicit static routes pointing to the ILB forwarding rule IP. The Azure approach is the most operationally lightweight from a routing management perspective. For cross-VNet and cross-account sharing, AWS allows a service provider in one account to share gateway load balancer endpoints across accounts using private link. Azure supports cross-VNet chaining natively. GCP's model requires shared VPC or explicit VPC peering configurations for cross-project inspection. All three platforms support flow affinity for stateful inspection. AWS uses a 5-tuple hash. Azure uses a 5-tuple hash as well. GCP's internal pass-through NLB uses connection tracking to maintain session stickiness. All three remove unhealthy NBA instances from the pool automatically based on health check failures. Decision Guide: Choosing the right platform. In this final slide, we consolidate the architectural insights from this series into a practical decision framework, the choice of which gateway load balancer model to use is driven by several factors: your existing cloud platform, the NVIDIA software you have standardized on, your operational model for route management, and whether you need inline blocking or out-of-band detection. If you are on AWS and need inline NVIDIA inspection with cross-account sharing, for example, a centralized security services account that inspects traffic from multiple workload accounts, AWS Gateway Load Balancer with private link endpoints is the native and recommended architecture. The Geneve encapsulation is well supported by major appliance vendors including Palo Alto Networks, Fortinet, Checkpoint, and Cisco. The main operational requirement is managing user-defined route entries in each application VPC, which is typically automated through CloudFormation or Terraform. If you are on Azure and value operational simplicity in traffic routing, the chaining model of Azure GWLB is compelling because it does not require route table management in consumer VNets. The dual VNI tunnel interface model is supported by the same major vendors. Azure GWLB is particularly well suited to scenarios where you are already using standard load balancers or application gateways as your consumer frontends. If you are on GCP, the answer depends on your use case. For blocking-capable inline inspection, deploy NBAs behind an internal pass-through NLB and use policy-based routing to steer traffic. For detection-only use cases where you need network visibility without introducing a potential blocking point in the data path, packet mirroring paired with an IDS collector fleet is the cleaner architecture. GCP environments often use both models in tandem: PBR-based inline inspection for egress internet traffic and packet mirroring for east-west visibility within the VPC. Thank you for your attendance. Please consider subscribing to the channel and liking this video.